Welcome, everyone. Thanks so much for joining us today. My name is Jennifer Rubin, and I'm the Vice President of Partnerships and Special Projects for the American Society of the University of Haifa. It's been a big week for physics, and specifically black holes, with Tuesday's announcement that 3 laureates would share the 2020 Nobel Prize in Physics for their discoveries about one of the most exotic phenomena in the universe, the black hole. On the heels of this momentous award, we're fortunate to be joined by University of Haifa Professor Doron Chelouche to explore black holes, gravity's fatal attraction. Professor Chelouche is an Associate Professor of Physics and Vice Dean of Research in the Faculty of Natural Sciences at University of Haifa. He's also the Director of the Haifa Center for Theoretical Physics and Astrophysics and a founding member of the university's Data Science Research Center. He's currently leading a unique project to map the immediate environs of supermassive black holes, aiming to understand the properties of such objects out to the edge of the observable universe. His research has been supported by NASA, the European Union, the Israeli Committee for Planning and Budgeting, and the German Research Foundation. He has recently received funding from the Israeli Science Foundation to construct a first-of-its-kind research telescope, which will be located in the Negev Desert near Mitzvah Ramon. Professor, before I turn things over to you, I'd like to remind the audience that you can submit questions through the icon at the bottom of your Zoom screen, and we will do our best to address them all during the Q&A portion after the presentation. Professor Chelouche, over to you.
Thank you very much, Jen. Thank you very much, and welcome everyone. Welcome to my home. Nowadays, this is what we have in COVID days. I have a dog, so if you see a dog running around, don't be scared. He's harmless. So let me just share the presentation with you. Go to rehearse mode. And okay, so the topic of our talk today is about black holes, gravity's fatal attraction, and it happens to coincide with the most recent Nobel Prize that was just awarded 2 days ago. By chance. So what you see here in this picture is the crater in Mitzpe Ramon. It's an overlook from the observatory, from the WISE Observatory at Mitzpe Ramon. The telescope that this work is based on, you see the dome of the telescope to your left, and you see the sunset, the beautiful sunset, and the crater of Mitzpe Ramon is just beyond those nearby mountains. So as you can see, there's a tiny Nobel medal that I introduced here after the announcement about the Nobel Prize in Physics, which is very much related to the topic of our talk today. So black holes are essentially everywhere around us. And what do I mean by that? Well, nowadays we go to Google to understand what's going on. So what I did was just punch black holes on Google search engine, and I got 500 million hits about black holes. If you want to compare it to something else, then if you do the same for COVID-19, you get 5 billion. So between COVID-19 and black holes, there's only a factor of 10, which means black holes are really everywhere online, at least. So that's to show you that black holes are indeed all around us. Now, the term black hole was coined not by a physicist, but rather by Anne Ewing, who was a scientific reporter who reported some theoretical advances in physics. And she was the first in 1964 to publish an article coining the term black holes, which then made it through physics, through popular culture, and everywhere, basically. Now, when we think of black holes, it very much depends who you ask. For example, it's part of jargon these days. You have political black holes. You have economical black holes. And to quote Johnny Depp, for example, for him, religion is a fascinating black hole. So the concept of black hole extends much beyond physics and science. You also see black hole fashion. For example, a black hole printing on a shirt, or even nail polish and coloring and painting, which is like a black hole. We'll see it later on too. Black holes are also very much part of popular culture. You've had a movie about black holes already in 1972 or 3, I think. In the middle panel, you see the Enterprise spaceship about to be swallowed by a black hole, and the Simpsons are running away from a black hole. So it's indeed part of popular culture. Arts and design. Yes, in a museum, you have a black hole on the left, and on the right, you have a carpet with a printing of something which looks like a funnel leading perhaps to a black hole. But if you ask physicists what they think black hole is, then they will tell you it looks something like that maybe on the left. This is a model. And on the right, you have equations. So depends on whom you ask what black holes are, you would get different answers. And what I would like to do in this talk is actually give you the physicist's perspective of what black holes are, specifically supermassive black holes, as we call them, and specifically what we are doing at the University of Haifa to study them. And to do that, we'll go into a corridor which has 4 doors. And you know the acronym. The acronym is American Society of the University of Haifa. But the acronyms that I will be using are a bit different. So let's open the first door. The first door, I call it ambition. And this is basically to understand what motivates physicists. What motivates physics? What is physics? So basically, physics attempts to explain the physical world around us. It can be why an apple drops to the ground, why stars exist, why we as human beings function, what makes our biology. Biology is also based on physics. Why does a building stand and doesn't fall down? So everything, underlying everything, our physical world is actually physics. Now, what is important to say about science in general and physics in particular is that physics relies on quantifiable observations to motivate it. For example, I look at the stars, I see the stars moving on the sky in a particular way, and then I'm trying to deduce some physical principles that would tell me why those stars behave like they do. So physics, unlike mathematics, for example, which does not really care about the physical world around us, it doesn't aim to explain the physical world. Physics has really no place if it doesn't try to explain what we see, what we measure in the world around us. And once we think that we deduced some physical laws based on observation, and we try to do it as simple as possible rules for us to be able to comprehend it, but not too simple so as to not explain what we see. Once we do that, we try to take the theories that we constructed, as simple as they may be, and implement them, for example, to a different system, and try to see and get theoretical predictions for a different system. For example, if I think I understand how gravity works on Earth, I would try to see how to implement it to the gravity that works in other planets or stars. And presumably, hopefully, the physics that I deduced locally on Earth applies also beyond the limits of Earth in the solar systems, galaxies, the entire universe. Now, then comes the crucial step. We try to test the theories with observations. So if a theory isn't able to explain the observations, then there are 2 ways. Either we try to correct it, because we say it might be incomplete, so there are some corrections to be made and new theories to gradually develop, or we simply change our entire perspective of what physical theory is, which happened quite a few times in the history of physics. But the ability to test the theories with observations is crucial for doing science and for explaining the world around us. Now, why do we do physics? I'm often asked this question, and to tell you the truth, it's not an easy reply, but I think that the most candid reply that I can give you was actually well, in some ways, in a heuristic way, was given by Feynman, who was a very great physicist in Caltech. And he said something which is something of the sort. Physics is actually, why we do physics? We do it because it's fun, because we like it. We don't necessarily do physics because we think it will give us some benefits in the nearby future. We do physics because we try to explain what we see, because we're trying to push our frontiers of knowledge, not necessarily because we think we're going to gain something in the immediate future. However, having said that, I will just note that all the computer world and internet would not exist if it were not due to a few physicists at the end of the 19th century and the beginning of the 20th century that were bothered by some very abstract questions concerning some obscure theory, which is called quantum mechanics. So nobody knew really what they're working on. They were working on it among themselves, entertaining themselves. But this theory of quantum mechanics, a few decades later, completely changed our understanding of the universe and allowed for computers and all kinds of semiconductors to be developed. And now the quantum revolution that you may have heard about, and quantum computers and quantum supremacy and all those things. However, what motivated those physicists to do physics was something which was completely abstract. Okay, who's who in physics when it comes to black holes? So when it comes to black holes, usually people quote Einstein, for example, as one of the fathers, the founding fathers of the theory underlying black holes. But in fact, to understand black holes, we need to understand two things. We need to understand the nature of light, the physical nature of light, because we're talking about black holes, meaning that they do not emit light. We'll get back to it. So we need to understand what the nature of light is. And we need to understand what is the nature of gravity. And this Einstein told us in 1915. Combining our understanding about the nature of light and the nature of gravity, we can do something with black holes. And what you see here is Carl Schwarzschild on the right, who actually got the first solution, real solution for black holes. However, I will not concentrate on these three fantastic physicists and eminent scholars, but rather on predecessors to them, which relate to the classical view of what light is and what gravity is. As far as light is concerned, Ole Romer is on the left, 1676. You have Isaac Newton at 1686, and combining their knowledge, John Mitchell, a reverend, in 1783, was actually the first to discuss what we now term as black holes. And this was an interesting historical anecdote. So I will concentrate on these three figures to try to explain to you what black holes are all about. So let's first concentrate on Newton. And of course, you all know Newton and the fact that the legend that he was sitting under an apple tree and an apple fell and he discovered gravity. Essentially, what Newton said is that gravity works between any masses. For example, the moon and the earth, but not only the moon and the earth. For example, myself, I'm also massive, and the earth, between people even, because people are masses, if you think about them. Not only masses, but they're also masses, so gravity works between them as well. It's simply so weak that we cannot sense it and measure it. But gravity works between any kinds of masses, and it's an attractive force. It tries to pull those masses together. Now, what Newton realized, and what we shall see, is that the taller the tree from which the apple falls, the faster the apple would hit the ground upon release. And this is exactly what happens when you take a very heavy object and you throw it from a meter height or 2 meters height or 10 meters height. The higher you will raise it and let it fall to the ground, the higher the terminal velocity is when it hits the ground. Specifically, if I try to take the tree and create an infinite tree out of it, so the canopy is at infinity, and see how fast the apple hits the ground, it will hit the ground at an astonishing speed of 40,000 kilometers per hour, which corresponds to roughly 11 kilometers per second. This would be the speed with which the apple, released from an infinite canopy at infinity above the Earth, this is how fast it would hit the ground. And I'm neglecting all kinds of drag forces in the air, etc. Now, what is interesting about Newtonian physics is that you can shoot the movie of the apple falling down, but you can actually play the movie in reverse, and the physics will not change at all, which means the following. If I take an apple and I kick it up with a speed of 40,000 kilometers per hour, or 11 kilometers per second, if I kick the apple fast enough, the apple would be able to reach infinity and basically escape the gravitational pull of our planet, as you can see here. So this is what we call the escape velocity from a body, let's say from the Earth. If I give the apple a velocity of 11 kilometers per second or higher, it would reach infinity. If I give the apple a lower velocity, a lower initial velocity, it will not be able to escape the pull of the Earth, which is why when I throw an apple at a much lower speed than 11 kilometers per second, it falls back. So this is the concept of escape velocity, and this is crucial, the first crucial step for understanding the physics of black holes. Now, the escape velocity is not some constant of nature. It depends on the body from which you want to escape. So for example, here you have three objects in the slide. You have the Earth on the left, top left, from which the escape velocity is, as we said, 11 kilometers per second. Much smaller than this on the bottom left is the Moon. And this is roughly to scale. The Moon is much smaller, it's much lighter than the Earth, and the escape velocity is only 2 kilometers per second, which means I only need to kick an apple with 2 kilometers per second for it to escape the Moon. Jupiter is on the right. It's the most massive planet in our solar system. It's very massive, it's very big. The escape velocity is much larger, 60 kilometers per second. And this begs the question of what really sets the escape velocity. And for this, I want to take you through a journey of what it means to actually do physics. Now, I know many of you haven't studied physics, but let's try to do some physics nonetheless. And the first thing that we need to go to is the second door in our corridor, marked by the S. And the S stands for structure. To try to do physics, one needs to understand the structure of physics. And physics is a very structured language, which is based on mathematics. And I will show you a few scary slides now. And this is the first scary slides. You see all kinds of weird equations on this slide. On the right, you see some page from a physics book. And many of you are not accustomed to that, and the symbols are weird. You can identify some letters, but not all of them. But what I want to teach you is a trick. And this trick will allow you to open any physics book and immediately understand what physics is involved just by looking at the equations. And what you need to pay attention when you open a physics book is for a few main letters of the alphabet, which are the following. The first one is the letter H with a bar on top of it, and this is called H bar. It is called Planck constant, and when you see this letter, this character, it immediately tells you that it involves quantum mechanics, quantum theory. And you see on the page to the right, on the image that I took from the page on the right, you see that this H bar exists. So this means that the book on the right is related to quantum theory. Now, another constant, another letter which is important to note is the capital G. This is Newton's constant. Whenever you see this constant, it means that we're talking about gravitational physics, about gravity. So if you look at the equations on top there, you see the topmost equation, it has the letter G, which means it is related to gravitation. The last character that you see is the letter C, and this stands for the speed of light. When you see that, it immediately tells you that you're talking about Einstein's relativity or electromagnetic theory, basically light. So, for example, in the top equation that you see, which included the capital G, Newton constant, you also see the letter C there, which means that this equation is part of Einstein's relativity related to gravity, because it includes both the G and the C. And this is indeed one of the equations of Einstein's general theory of relativity. So just by looking at those few characters, you can immediately tell which physics is involved. And when it comes to calculate the escape velocity from a body, I can immediately tell you that whatever expression we will get for the escape velocity must include the letter G, the Newton's constant, because we are talking about gravity. Okay? The escape velocity is all about the gravitational pull, and so whatever expression we get for the escape velocity must include the letter G. Okay. Let us now try to actually find the escape velocity, find the physical equation for the escape velocity from a body. And when I say a body, let's make it simple. Let's take a sphere, and this sphere is of size r, let's say. It could be the radius, could be the diameter. I don't care about that much right now. Let's take the radius of this sphere. It's like a ball of some mass m and some radius r. It could be a planet, it could be a football, it could be the sun, it could be many things. This is an object. And I want to calculate the escape velocity from this object. And so I know what speed I need to kick the apple with for the apple to escape the ball. Now, what is interesting about physics is once you know what quantities you can play with, what are the important quantities to deal with. In this case, it's the radius of the sphere, the mass of the sphere, and we know that Newton's G constant must be there. Once you know which variables you have to play with, it's now like solving a puzzle. It's just putting the puzzle bricks in the right way to get the correct equation for the escape velocity. And what I want to go with you now is through something which is called quantity calculus. Each physical parameter that we have in nature has some physical units associated with it. For example, mass. Mass we can measure in kilograms or grams, but these are the units of mass. Length, for example, the radius of this sphere we're talking about, is measured in meters, like we measure distance. G is a bit more complicated, it's a bit weird, it has weird units, but I will give you the units and you don't have to bother yourself with that anymore. The units are meter to the power of 3, which is like volume, divided by mass, times time times time. Okay, so it's meter to the power of 3 divided by kilogram times second to the power of 2. Again, it's weird, but believe me, these are the units of this G constant. Now, we want to play with these parameters to get the escape velocity. This is what we need. We need the escape velocity of the apple. And to do that, we need to somehow combine these parameters to give us an expression for the escape velocity. So let's just try to try some kind of an equation of the following form. Let's assume that the escape velocity equals m plus r minus g. Now I can immediately tell you that this expression is wrong. And why is it wrong? It's wrong because of a very simple reason. When I try to add radius to mass, it's as if I were trying to ask you or add 3 kilometers per hour and $3. I cannot, or 3 degrees Fahrenheit and $3. Those different quantities do not live in the same space. I cannot just add 3 degrees Fahrenheit and $3. It doesn't work like that. They don't live in the same space. It's meaningless. I can only add quantities whose units, measurable units, are the same, like $3 and $3. Or some conversion factor, like $3 and 3 pounds after I convert the pounds to dollars. So this equation that you see here is simply wrong. It cannot be a physical expression that leads to, that will tell us what the escape velocity is. We can try a different combination, and the different combination we are trying now is to take m and divide it by r. Now, if you look at the physical units of this expression, m divided by r, the mass m is measured in kilograms, the radius r is measured in meters, so I get physical units of kilogram over meter, kilogram per meter. I'm not exactly sure what the meaning of these units is, but let's try to see what the units of the escape velocity that we need is. And the escape velocity is a unit of velocity. It can be length over time, can be kilometers per second, can be meters per hour, but it's length per time, length per unit time. So you can see that on the left side, I want to get units of length over time, but on the right side, I have units of mass over distance, kilogram per meter. And those units on the left and on the right part of the equation simply don't end up. They don't add up. So this cannot be the expression that gives you the escape velocity. But let's now try to multiply it by the g constant of Newton. If we do the unit calculus, the quantity calculus, and we now look what are the physical units that we have on the right side, we will get length squared divided by second squared. That is distance squared divided by time squared. On the left, we need distance by time or length by time. So the units don't exactly match, but what we can do is take the square root. And when we take the square root, we get almost the correct expression for the escape velocity from a body whose mass is m and whose radius is r. If we were to do the real physical calculation, there will be a factor of 2. But we did a physical exercise now of finding the escape velocity from a body, actually with knowing very little physics, just making sense of the dimensions of the variables that we're working with. So this is just a quick way of communicating to you what doing physics is all about. So this is the escape velocity from the body. Now, what is interesting about it, that if you look at this expression, V escape equals the square root of 2 times g times the mass divided by r. Let us now make an experiment. And this would be a theoretical experiment, a Gedanken, as they say in German. And let's take a body. And let's assume that the body has a certain mass, which I'm not changing at all. All I'm doing now is taking the body and just squeezing it. And by squeezing the body, I'm making it smaller and smaller and smaller and smaller still. So the radius of the body shrinks. If you look at it now, as the body shrinks, r becomes smaller. If you look at the expression for the escape velocity, r is what is in the denominator. As r becomes smaller, the escape velocity from the body actually increases. And as the escape velocity increases, in principle, you could get to very high speeds. You will need to give the apple not 11 kilometers per second boost to escape Earth. If the Earth were much tinier, the escape velocity could be much higher. Now, what Ole Romer told us already in 1676 is that light travels at a finite speed of 300,000 kilometers per second. It's an astonishing speed, but this is the speed of light. Later, Einstein also told us that this is the maximum speed that is available in the universe. You cannot reach a higher speed, but that's a different, extremely important topic, but I will not have time to discuss it. You can ask me later in the questions section. Now, this means that at some point, as I shrink the mass, the ball, to extremely small scales, I can reach a scenario in which light, even light, will not be able to escape this sphere when it is emitted from its surface. For example, Earth will become black hole if we're able to squeeze it into 1 centimeter in diameter. It will just shrink and then fade away. You will not see it anymore because light will not be able to escape it. You can do the same with a person. If I'm a person and someone squeezes me into an unbelievably small dimension, which is much less than the size of atoms, of even protons which comprise them, then even I could become a black hole. No one would see me because light emitted from my skin will not be able to escape my skin if I'm squeezed to such tiny dimensions. So the implied material densities and pressures that are required to make the Earth or me a black hole are things that are very much beyond what we can achieve in the laboratories on Earth. And black holes are nowhere to be found on Earth. And the question, of course, is whether black holes exist somewhere else. And now I come to John Mitchell, the Reverend Mitchell, and I went through his writings, and it's quite amazing that already more than 200 years ago, he says, if any other luminous bodies should happen to revolve about them being dark objects or black holes, we might still perhaps, from the motions of these revolving bodies, infer the existence of the central ones, which means the black holes, with some degree of probability. So this was already in 1783, and what I want to show you now is that John Mitchell was right. But to show that it was right, it took us more than 200 years to get to it. And what I will show you now is the following. I will show you an animation. It's not an animation, it's actually footage. It's a movie based on images taken at the Very Large Telescope. And this result was actually one of the main reasons for awarding the recent Nobel Prize in Physics to Reinhard Genzel and collaborators, Andrea Ghez. And what you will see here is points on the sky. Each point is actually a star, like our sun. It's very, very far away. And each of those points is a star like our sun, and about it you could have planets as well, only we cannot see them because they are too faint. And I will show you a movie that looks at this patch of the sky and the motions of stars on the sky and follow them for 2 decades, and you will see how those stars move about. Now they move about, because the stars are so far away, they move about with amazing speeds of thousands of kilometers per second. And here you see an animation based on those stars. And if you look closely and see what objects those stars are revolving, you will see that they revolve around an object which we simply cannot see. We cannot see anything about in the directions around which the stars are revolving. And we looked at the deepest telescopes, the strongest telescopes, and we couldn't find anything. And this black hole, what we think is a black hole with very, very high probability, has a mass which is astonishing. It's about 4 million solar masses. That is, take our sun, multiply its mass, which is extremely high, by 4 million, and you will get the mass of this black hole. Now, this black hole lives at the center of our galaxy, and this was the reason for awarding the Nobel Prize in Physics, for detecting such a huge black hole for the first time at the heart of our galaxy. I will show you immediately. So this black hole exists in our galaxy. And our galaxy is just a huge collection of stars, 100 billion stars that we live in. And this is the Milky Way galaxy. And where I circled in red, this is the direction of the center of the galaxy as we see from the southern sky. Now, because we live in this galaxy with the white fuzz that you see is just a huge collection of stars that we cannot resolve them individually, because we live in the galaxy, we cannot see it from the outside. But if we were to look at our galaxy from the outside, it would probably look something like that. So this is our galaxy as this is a galaxy similar to ours. And you see, I marked more or less where the solar system might be in this galaxy. And I marked also the center of this galaxy. And the center of this galaxy is our own center of our galaxy, is where this gigantic black hole resides with 4 million solar masses. Now, the distance between us and this supermassive black hole that I just showed you is huge. It's about 1 quintillion kilometers, one with many, many zeros, 18 zeros afterwards, kilometers. So it's very, very far away. It doesn't affect us directly at all, okay? But just to show you what scales we're talking about. And it's not the only thing that we see. We see black holes also in other galaxies like M87 galaxy, another galaxy for which we see a black hole. And then it comes down to the following questions. Can we generalize from 2 convincing black hole examples in the universe and say something about black hole population as a whole? What is the physics of these extreme objects? How did they came to be at the centers of galaxies? And can the black hole at the center of galaxy affect us at all? So these are very fundamental questions to ask. And it turns out that most of our knowledge about those huge beasts, huge black holes, come from the fact that not all black holes are actually black. In fact, it turns out that episodically, those black holes are able to accrete, to get and swallow mass from their surroundings, in which case they brighten up and we see material shining from their immediate vicinity. This is before the material plunges into the black hole and then we cannot see it. But before it does so, before it reaches the surface, let's say, of the black hole, we can still see it out to large distances. So we know there is a black hole there. We cannot see the black hole because it's black, but we know, we see the signs of a black hole and what it does for the environment. Now the problem is that we cannot really resolve what's happening close to the black hole because those black holes are so far away. They're so far away from us that we cannot resolve their structure. It's like we cannot see the 2 headlights of a car which is very far away because we don't have the resolution for that. If we had very big telescope, we would be able to do that. So this is why there is a race in astronomy to go for big telescopes. But we cannot observe them directly. We cannot see what's happening, the feeding process of black holes. And if we were able to understand that, we would be able to understand a lot about black holes, how they came to be so massive, how they affect their galaxy, whether they affect us at all. The only thing that we can see from this very cute simulation that I've shown you, and now I show you an image from that, we only see a big fuzz of light. We don't see much beyond that. When we monitor and look at this fuzz of light for a long time as a function of time, that is, we take a picture of this source every day, we see that the light varies with time, which gives us a lot of information, but not quite information that we need about the structure of the material around the black hole and how much of the material is swallowed by the black hole and the physics of the black hole. It gives us some information, and the information tells us that it's likely, our models at least say that the material that is funneled into the black hole is probably revolving in some kind of a disk around the black hole. But we cannot really understand what's going on. We cannot really tell whether it's a disk or not. These are models. But as we said, models in physics must be tested to do actual physics. And then improve the models or completely change the theory. Now, what I want to show you is to go to the third door in our corridor and give you an update of what we've been doing at the University of Haifa regarding this problem, trying to image what's going on very close to the black hole, supermassive black hole in galaxies, especially in those objects which are episodically accreting, swallowing mass from the environments, and we can actually spot that there is a black hole nearby. So mapping the immediate environment of black holes is tough. It requires the biggest telescopes on Earth. And this is one of the biggest telescopes, the VLT, for which Reinhard Genzel was doing his observations of the black hole in the center of our galaxy. And for these observations, he has been awarded the Nobel Prize in Physics. But I would want to show you that we can do very competitive science, not with those huge telescopes, but rather with a tiny 40-centimeter telescope at Mitzpe Ramon at the Negev Desert. And I will try to convince you that we can even do better in some ways than those big telescopes. And to understand the basic idea behind it is the concept of reverberation mapping or echo mapping. So I want to take you to a concert hall, and this concert hall, you have a piano at the center. Now, the piano makes a sound, emits sound waves in all directions, and there is a sound wave that goes directly to you, the audience. However, there is another sound wave. There is a sound wave that is emitted not in your direction, but actually to the side. So you first hear the one that comes straight from the piano, but there's a sound wave that is reflected off the wall, and you hear it as an echo. What is interesting is that if you are able to hear the direct sound from the piano as well as the echo, if you're able to hear them and quantify them, no matter how far you are from the actual concert hall, you can actually understand something about the geometry of the concert hall by echo mapping. And this is exactly what we're doing, only we're doing it with light. Now, this seems to be a bit strange because we're not too used to the concept of light echoes, but this is just because light travels so fast and our eyes are not very good instruments. But if you were in the concert hall and instead of a piano, you would have a light bulb that turns on and your eyes were extremely sensitive, you will be able to see, first of all, how the light reaches only the extreme vicinity of the light bulb and then reflects back to you. And as time goes by, you will see more and more of the concert hall, and you may also see the organ, for example. So if we were to look at how the light intensity is as a function of time, let's say at some particular time someone turned on the lamp, the light bulb, and now it shines in blue light. It will take some time for us to see, for example, the light from the organ reaches us. The light from the organ is silver. And if we were able to really test the time delay between the time that we see the direct light from the light bulb and the silver light from the organ, we would see a very short time delay between the two signals. And this short time delay is just a measure of the size of the stage, if you wish. And by measuring this echo, you're actually measuring how much time it takes the light to travel across the stage, from the light bulb to the organ and then back to you. So if you find light echoes, time delays between light echoes, you can actually say something about the geometry of the stage. So what I'll show you now is what happened a long, long time ago in a galaxy far, far away, as the movie says, or more physically about 500 million years ago in a galaxy called Markarian 279, which we observed at the WISE Observatory, and you see here marked the galaxy. And what we did was try to understand what is the immediate environment of the black hole, how it looks like. And to do that, we took not only the images of the galaxy in a particular color let's say blue in this case, and plotted how the light changes with time. If you look at the x-axis, this is time in days since April 2018. And on the ordinate, the y-axis, you see the flux that we measured, how much light we saw from the source, and you see that it goes up and down. But we also measured it in other colors. We measured the light in several colors, from blue to green to yellow to red. And what you see here, if you were, for example, look at how the light changes in the blue and how the light changes in the red, you will see that there is a small but finite time delay of about 2 days between the fluctuations in the blue light and the fluctuations in the red light. So basically these are the light echoes. So what do we find? How do we interpret the signal, and what do we find? So I won't go into all the bother you with all the details, but I will just let you now show you the results that we find for the geometry of the concert hall, that is, as if the geometry of the material around the supermassive black hole. On the bottom right, I show you the current theories. And in the main part of the diagram, I will show you what we found. So what we found is that indeed, in the central part, very close to the black hole, there is some kind of a disky structure where material is gradually being accreted and swallowed by the black hole, which is at the center. However, on slightly larger scales, we see actually a very different picture to the classical models, where we have gas which is not falling in, but actually flowing out of the region of the immediate vicinity of the black hole. Let's look at a different projection, which will make it a bit easier to understand. And this is when I tilt the inner region a bit towards our sightline. The classical picture on the bottom right tells you that the theory predicts that it's just a disk structure, like a plate revolving around the black hole. What we find is actually it's more like a cup. There is also a cup that goes up as if, and material is actually outflowing from the vicinity of the black hole. I'll show you yet another projection of that where the cup is more visible, and it goes up to very, very great heights above this disky structure. Now, maybe to you it's not very obvious what it means, but I will tell you briefly what it means. First of all, it means that some of the black holes are actually hidden from our sight. Because if you look at the bottom right, you see that there is this red region that theory predicts that shines, and you can see it. But if you look at the main picture, which is the new geometry that we infer from our reverberation mapping studies, we see that we do not see the central region. If we're at an angle, at high enough angle, we see the central region. But if we are too inclined with respect to the disk, we do not see it. This means that there are actually many, many more black holes than that currently accrete material, only we don't see them. So this completely changes our statistics of black holes that accrete material, and therefore understanding how black holes actually grow with time by accretion of material. Another thing that is interesting about this picture is that some of the material is actually outflowing and not ending up in the black hole. And this means that our initial estimates for how much black holes swallow mass as a function of time and hence grow is incomplete and needs to be revised. So we don't understand how black holes grow in the universe, and we need to update our numbers and update our theories. So this is something which was very surprising to us. And let me just show you quickly what the scale is. I've been talking about the structure, but I haven't talked about the scale. You will see on the left side, you will see our solar system. So I just want to show you what the size of the solar system is compared to this gigantic structure that you see here. So as you can see, it's a tiny, tiny little structure. So we were able to find and map the structure in the immediate vicinity of a black hole, which lies in the center of a galaxy, which is itself very far away from us. And we did it in a way which is equivalent to you in the US, for example, being able to measure a single hair on my head while in Haifa, and not via Zoom. So to do so would require an effective telescope whose size is about 100 kilometers. And we don't have anything like that. So this is just to show you that if you have anyone, if you use the right technique, you can do very competitive and science also with very small telescopes. It's just finding the correct means to an end. And the results I've discussed here were published by Nature Astronomy journal in 2019. So the last thing I would like to tell you is to go to the last door in the corridor. And the last corridor is labeled Haifa. And what I would like to interest you is in the following endeavor, for which we are now looking for funding. And this is a campus observatory as part of a hub for public outreach programs at the University of Haifa. So this is tightly related to astronomy, although not to research. It's actually for public outreach program at the University of Haifa. And this is just a picture of what it might look like if the observatory were to be erected on top of the Hatta student building. Now, roughly, let me just give you the rough numbers. We are talking about something like $100,000 or so for the observatory, grosso modo. These are the numbers. So why at the university? First of all, because we want to cultivate the next generation of scientists by exposing pupils, the younger generation, to leading researchers in their respective fields, not only in astronomy, but also in physics, also biology, all disciplines of science. And to tell you my personal story, I actually went into science because of similar activities run by Tel Aviv University when I was young. So this was, for me, it was amazing. And second, because we need to promote the university's scientific profile, and we need to do that not only for the natural sciences and exact sciences, but also for the marine sciences and data sciences and environmental sciences. And this is crucial. Third, because there's no other higher education institution in the northern part of Israel that does so. So we will be the only ones to match a need in this case. And let me do what we have been doing so far without this observatory. So we've been doing, in pre-COVID days, we've been having public lectures on various kinds of science, whether it's physics, biology, with 100 or so regular participants of all age groups, senior citizens, kids, students also, even faculty, but most of them outside the university. These are freely monthly events that includes a talk as well as an astronomical observation with a very small telescope near the multi-purpose building. And the activities are completely run by volunteers as part of the Haifa Center for Theoretical Physics and Astrophysics, but we want to get it to the next step as part of a real hub for science and public outreach at the University of Haifa. Now, broadly speaking, what you will see is inside you will see a telescope. There will be a dome protecting the telescope, and there will be visitors coming into the telescope and observing through the telescope. One will be able to observe galaxies, the moon surface, citizen science projects. This is not very common in Israel. We want to approach it as well. Near-Earth objects to protect the Earth from asteroids. We will be able to watch, to observe nebulas, planets, solar flares with a solar telescope, and even satellite communications. All those things can be a true hub for the general public as well as students in the university through various programs like Perach programs, etc. And let me just give you the last slide. So we want to construct an astronomical observation on the Carmel campus, where we have less air and light pollution compared to downtown. There are two potential sites, one that I showed you on top of the Hatter student building, which is viewable from the entire Bay Area of Haifa, and it can really be a focal point seen by everyone at the university and outside the university. Another option B, which is less favored, is close to the multi-purpose building. The only issue with option A is the stability of the structure, and this needs to be figured out with engineers. We haven't done so yet. Basically, we're talking about a 0.5 meter telescope with computer-controlled dome and all the necessary equipment, as well as a solar telescope. And I think with all the schools and buses that come with pupils that come regularly to campus, this could really be a focal point for public outreach at the university. So let me sign off here, and thank you very much for your attention.
Thank you, Professor, so much for explaining things in such a relatable way. If you don't mind, with the time that we have left, I'd like to launch into just a few questions.
Yes.
Excellent. Okay, so to start, could you elaborate just a bit more on the recent announcement concerning the Nobel Prize in Physics?
Yes, definitely. So I think so basically the Nobel Prize was divided in two. 50% went to theoretical advancements, and 50% went to observational advancements in the field. So basically, as far as observations are concerned, it was given to Reinhard Genzel and Andrea Ghez for what I've talked about, basically. The first detection of a very compact object at the center of our galaxy with masses that are enormous. And this was totally unexpected. And these observations, as well as follow-up observations, actually showed us that basically there is no alternative explanation, or we do not know of any alternative explanation but for a black hole at the center of the galaxy. This was a major surprise because we think we understand how small black holes are formed. We do not know how these ginormous, gigantic black holes at the centers of galaxies are formed. So this was, and they affect the entire structure of the galaxy. They affect how the universe is evolving. And this is very interesting. Now, as far as the theoretical part, this was given to Penrose for actually telling us that black hole, or the formation of black holes, is an expected evolutionary track in the lifetime of our universe. Because the notion of black hole that came out of Einstein's theory of general relativity, which is the true way to actually deal with the problem of black holes, tell that there is a solution of a black hole to Einstein's equations. But the fact that there is a solution doesn't mean that it's really physical. How to form a black hole? What Roger Penrose showed us is that there is a very natural way to form a black hole, and it's even inevitable. It's not very sensitive to how you start to form a black hole or to small deviations. And this was the strength of his theory that told us that black holes do not only exist as mere theoretical solutions, but there is a theoretical formation path to them, basically. So for those two major breakthroughs in gravitational physics and black holes, they got the Nobel Prize.
Okay,
Yes.
Thank you. I know we're running short on time. I want to get to a couple more questions. So if you could help me with, does the fact that we don't see anything in some direction in space around which the stars orbit, does that necessarily imply a black hole? Or can it be something else that simply doesn't shine?
Okay. Let me say that until 2 decades ago, or a decade ago, it is true that we could only say that such and such dark object is not stars, is not gas, is not lead, is not concrete or other things. Lately, because of the works of Reinhard Genzel particularly, as well as additional very recent observations which are not part of the Nobel Prize, we have been able to resolve the immediate environment of two black holes, very nearby black holes, to the degree that our theories do not have any other alternatives to black holes, which means basically we ruled out all the known alternatives to black holes. So what we can say right now is that all the observations are consistent with black holes as predicted and envisioned through Einstein's general theory of relativity, with works leading to today. Yes.
Thank you. Thank you. Okay, so science fiction often mentions wormholes as passages to other universes or other places in our universe. Sometimes we're hoping that maybe there's some additional options. Is there any evidence of this or for this?
No. I mean, theory, yeah, that's a short answer. Some theoretical work has shown that these things could maybe, in principle, exist. There are even theoretical problems with traveling through a wormhole, because it's likely that you will be crushed while moving through a wormhole. There's no observational evidence for a wormhole. So again, this is to be tested. One of the more things that theory needs to be tested with observations at the end, at some point. Yeah.
Thank you. And what might happen if a black hole passes too close to us?
Okay. It really depends on the size of the black hole and how fast it travels. If, for example, you might have a black hole which shoots very quickly near you, not too near you, but so you might not feel much. Maybe there will be a small nudge, but you won't feel much. If, however, you have a black hole that travels slowly next to you, then you can get swallowed by the black hole, and there are two options. One of them is nicer than the other. I mean, not that anything is nice, but in one of them you won't feel much until you are actually hitting the most central part of the black hole. Basically, you won't be able to communicate with any of your friends. You will lose sight of the universe, and you won't be able to escape the black hole, but you will go all the way to the center. But before you hit it, you won't sense much. However, there's another alternative. If the black hole is slow enough and small enough, then you might feel some tension growing, what we call tide. So, for example, your legs will be sucked in first and then the rest of the body. It's like a noodle. So it's not a pretty picture, but yes, please stay away from black holes if you can.
Oh, okay, we'll stick
unless they're fast, unless they're very fast, in which case you can relax maybe.
Okay, good to know. Thank you. It looks like we have one more question coming in and time for one more. So what would we see if we were to visit your office or your lab in Haifa?
I might even be able to show you. It's actually very, very boring, I must say. because we physicists now, much of our astrophysicists, much of our, sorry about that, much of what we do now is completely computerized. So we get information on our computer from the telescope. We do computerized simulations of nature. I guess the only thing that I can really boast about is the gefilte fish pillow that I have on my couch, which you can see in the picture on the left. But that's about it. So it's pretty boring, I must admit. Yeah.
Okay. Well, thank you for that close look into your dwelling. Nothing like a black hole. Unfortunately, we are out of time. Professor Chelouche, thank you so much for sharing your expertise and bringing some light to this astronomical phenomenon. If you have questions or would like more information about today's presentation or anything related to University of Haifa, please contact us at info@asuh.org. I'm sure Professor Chelouche would be happy to entertain any additional questions that we didn't have time to answer. If you would like to support Professor Chelouche's research, the Campus Observatory Initiative, the University School of Natural Science, or any other university faculties or programs, please visit us at www.astuh.org/donate. Thank you all for joining us today. Please be healthy and well, and we'll look forward to seeing you soon.